Okay, everybody, welcome to the compiler class, Compy 152. We have a very big class this semester. The last time I checked, there were 61 students enrolled. Um, so we have a challenge in managing a class that large. Okay. All right, so I see nearly 50 of you have already logged in. So why don't we go ahead and get started. Can everybody hear me?
Yes, sir.
Okay, very good.
Yes.
Great, thank you. And I'm about to share my screen. So let's see if that works. Okay, I hope you can see my screen now. Whoops. Hang on. Got a message here. All right. Okay, you can all see my screen, right?
Yeah.
Okay, very good. Yeah, I need to make sure because it's very hard for me to tell. Okay, let me open up the first set of slides here. This is 152. And yeah, this is who we are. Okay. Some basic information. I do have office hours every Tuesday and Thursday from 4:30 to 5:30. Earlier today, I sent out a Zoom link. So if you want to see me during my office hours, you can join the link. Okay. I do have a faculty webpage and a webpage specifically for this class. And let's take a quick look at it now. So this is my faculty page. I should point out that I am using a 30-inch monitor. And if you're looking at everything on a smaller screen, let me know if I need to increase any font sizes because as I said, I have a big screen, and of course it has to be shrunken down for your smaller screen. Okay, so this is my faculty page, and if you click on 152, you'll see that, gosh, I've already put up the first assignment, and I will try to remember to post my lecture slides for each day. And so the slides I'm about to show you, you can already download, okay? So go ahead and click on that and I'll download the slides, okay? Now let's take a look at the syllabus, okay? And okay, let's see. I do have an office, but of course, given the lockdowns, I'm never there anymore. Let's see. Oh, the goals of the class, okay? Two big goals. Number one is compiler construction and language design. I assume that most of you don't have a real clear idea of what a compiler is, other than it's sort of a magic box that takes your program that you've written in some high-level language like C++, and it somehow manages to transform it into something that you can run. And that's what a compiler does. And in this class, we will learn exactly what a compiler does. And not only that, you're going to write one. And you're going to be broken up into small teams. And each team, by the end of the semester, will have written a working compiler. And I know that sounds very scary. It is going to be a lot of work, but I rarely have a team that fails to come up with something that works at the end of the semester. And I've been teaching compilers at this university for the last 12 years. And so I do have a lot of experience getting student teams to actually write a compiler, okay? Now, the language design part is that, hey, if you're gonna write a compiler, then you get to invent a programming language, okay? So your compiler project and the one that each team is going to write, you can either write a compiler for an existing language, most likely a subset of an existing language. So maybe you might want to write a Python compiler, but of course, you're not going to have time to do the entire Python language. So you pick a subset, okay? But what's even more fun is you get to invent a programming language, okay, and write a compiler for it, which means you'll be able to write programs in your invented language, compile them, and run them. Because that's pretty exciting for a lot of students that not only are you going to write a compiler, but you're going to write a compiler for a language that you've invented. Okay, so that's where the language design comes in. Okay, now compilers, as you can imagine, are very large, complex programs, and so we're going to have to apply all our tricks that we've learned in good software engineering to manage to get a compiler written. And so I will give you lots of example code, and the assignments that you'll get, I think there'll be around 6 assignments, will help you to accomplish your compiler project. So at the end of the semester, you'll have a working compiler, and during the semester, the assignments that I give you will help you to actually implement this compiler project. Okay, so now, because it's a large, complex programs, and you're going to learn how to manage the development of such a program, you're going to learn a lot of skills that employers will want you when they're looking to hire you. Okay, so I know that the vast majority of you are not going to go out and write compilers for a living, but I hope that the software development principles that we employ in this class will help you with your other software projects. Okay? All right, so there are various learning outcomes. As I said, by the end of the semester, you will definitely know what a compiler does. You'll know how a compiler processes a program written in some high-level language and turns it into, code that the machine can actually execute. And then you'll also learn a little bit about machine architecture, because if your compiler is generating low-level code for a machine, then obviously you have to know something about the architecture of that machine. And there are various algorithms that compiler writers use, and of course we'll have to look at some of those algorithms, and that's the finite state machines, recursive descent. Those are all about the various algorithms that compilers use in order to do their work. Okay? There is one text which I will say is required. We're going to be using a tool called Antler. Okay? In fact, it's the 4th version of this tool. Okay? Compilers are, well, certainly not real compilers that you would deploy out in the field. They are rarely written by hand from scratch. Okay, modern compilers are written using various tools like Antler to help you to write these very complicated programs. And so there is a reference manual for Antler, and you really need to get a copy of this. I think it's not very expensive, like $35 or so. Because if you have to know how to use this tool, that's the bottom line. There is some material online, but it's not very complete, or at least I haven't found anything that's as good as this book. Okay. In the past, I've used this book, which I actually wrote. It's in its 3rd edition. I'm in the process of writing the 4th edition of this. And so the 3rd edition is a bit out of date, and last summer, I redesigned this course. So it's new and improved from the way I used to teach it. And the fourth edition, if and when I ever finish it, will reflect on the way I'm currently teaching it. However, the third edition does contain some reference material, especially about the Java virtual machine, which we will be talking a lot about. And if you can find a used copy or find it in the library, you may find some useful information. Although in class, in my lecture notes, I will give you most of what you need, and I'll point you to some online resources that will have the rest of the information that you need. Okay? But the first one, you really should get, and you can get it from Amazon. Okay. Now, in class, if I'm going to show you how a compiler works, then it has to be a compiler for a particular language, right? I mean, you use a C++ compiler for your work. Well, if I'm going to show you how to write a compiler, what language should that compiler be for? And so I've chosen a language called Pascal. Okay, now Pascal was the main teaching language in computer science and computer engineering during the 80s and 90s. So if we go back, 30 or 40 years, instead of learning C++ or Java in your computer classes, you would be learning Pascal. Okay, now so Pascal has important history. It's also a very simple and elegant language. Okay, it's simple in that the syntax is very straightforward. There aren't a lot of different types of statements, but it's still a very powerful language. You can write some very sophisticated programs in Pascal. Okay, now Pascal is not object-oriented, so it's kind of along the lines of C. Now, the C language is not object-oriented. So Pascal is not object-oriented. And that kind of fits in with this class because object-oriented languages have other complications for compilers, and we really don't have time to get into all those other more advanced topics. So we're going to use Pascal, and there are some tutorials. Either one of these will be good, and then you're going to want to get some practice writing Pascal programs. Obviously, if we're going to be looking at a compiler for Pascal, you ought to know the language Pascal. And so there are some online compilers that you can use. And so basically, each one of them, you cut and paste your program into a window, you push a button, and then it goes off to a server where the Pascal compiler on the server will then compile your program and run it. Okay, and so you'll be able to learn Pascal that way. In fact, your first assignment is to write some Pascal programs so that you'll be familiar with the language. Okay, I happen to like the last one, the JDoodle one, but the other two are okay also. Okay, all right. Now, there will be some software that you'll need to install. Oh, okay, I did not update this list. I thought I did, but and I'll mention the software as we go along. Now, there's the Macintosh, which I'm very familiar with. In fact, I'm on a Macintosh right now. I'm also very familiar with Linux. Especially Ubuntu. And so I would strongly encourage, if you're on a Windows machine, to install Ubuntu. And Windows 10 has made it pretty straightforward to install a version of Linux. And I, as I said, I'm most familiar with Ubuntu. And so you should do that. And then the tools like Antler, there are Windows versions of that tool, but I am most familiar with the Macintosh and the Ubuntu or the Linux versions of that tool. So I guess the bottom line is that you insist on doing all your development in Windows. That will work, but I won't really be able to help you very much if you run into problems, because I'm not that familiar with Windows. So, you know, out in the real world, unless you want to limit yourself to writing commercial programs, in the engineering and scientific world, you're going to find a lot of Linux platforms and Macintosh platforms. Okay? And so it's not a bad idea to get familiar with Linux if you're on Windows. Okay, let's see. Now, I guess the important thing here is that I've had a lot of students over the years tell me that the compiler class was the hardest software class they had to take. So that's kind of a warning that writing compilers is not easy, and it's going to take a lot of work. So be warned, okay? Let's see. Now, the team compiler project, as I said, you will work in small teams of 4, and each team will end up working on a compiler. And so that's your team, your semester project for each team is to write a compiler. And then during the semester, you will also be working on the assignments that will help you to write your compiler. And except for the very first assignment, all the assignments will be team-based. In other words, that each team will submit one assignment, so you'll work on it together. But the very first assignment, I want you all to work on individually, okay? And we'll get to that in a little while, okay? There will be a short report that comes with every a project, where you say a few words about, well, what is this language that you may have invented, say a little bit about how you designed the compiler and so forth. As we move on during the semester, you'll have a better idea of how to describe how you designed your compiler, okay? But that will go into a final report, a very short report, okay? Okay, here's how I plan to weight everything for your final semester grade. You see that most of your grade is going to be based on actual programming, you know, your assignments and your final compiler project, and that's the way it should be. I don't want this class to be you know, totally theoretical, and I want you to get a lot of hands-on experience, and so assignments and project will have a heavy weight, okay? And as I said earlier, the assignments and the project, except for the very first assignment, will be team-based, okay? According to department guidelines, the median total score will earn the B- grade, and then you know, the grades go up and down from there. You can keep track of your total score in Canvas. It will keep track of your score according to these weights, okay? And so I do grade on a curve, so what this is saying is that the middle of the curve will be the B minus. Okay. Now, at the end of the semester, each student will also turn in a short postmortem report that's like 3 or 4 paragraphs, very short. First paragraph, tell me what you learned. Second paragraph, tell me how you personally contributed to your project team. And the last paragraph, 1 or 2 sentences assessing each of your teammates. Okay. Now, the way I give everybody a final grade is that, first of all, a Canvas will actually calculate your total score. I line them all up, and the one that's in, the ones that are in the middle will get the B minus. Okay, that's the initial grade. And then I will go through and read each and every one of your postmortem reports. And if your teammates tell me that you were the project lead and you made sure everybody on the team knew what to do, then I will raise your grade. On the other hand, if your teammates tell me that you did not contribute, you didn't show up for any of the meetings, then I will lower your grade. That's so I will adjust the grades based on what your teammates tell me about you. Okay, so that says that being a participant in your team is going to be very important. Okay. All right, let's see. I think everything else is boilerplate. And then here is the schedule. I will try very hard to stick with this, although of course things can happen during the class, and I may get a little bit ahead or a little bit behind. But this is pretty much what I expect to cover each week. And then here on the right, you see that these readings are from that Antler book that I mentioned that everybody should strongly consider getting a copy of. Okay, and let's see, the midterm is March 18th, and we have a spring break. And I think I hope I've gotten the exam date correct, but I will double check that to make sure. You notice that in the very last week, we have project presentations. I'll have to see how we're going to do that, because with over 60 students, that means if every team had 4, we will have probably over 15 teams. And I don't know if we're going to be able to do that many presentations in over 2 lectures. It may take 3, but I'll work something out. Okay, and but I do want every team to have the opportunity to show off what they managed to accomplish in creating their compilers. Okay. All right. Any questions at all about what this class is all about and what we're going to do in this class? You can see we have a lot of things we're going to cover, and I'm sure right now some of this looks very cryptic, but you'll know what all these things are. Okay. All right. If there are no questions, at any time you have a question, just unmute and speak up, because otherwise I really can't tell. And it looks like there are a lot of chat messages. Okay. Okay, Antler reference, 2nd edition. Okay, the Antler reference, you want to get the latest version. Make sure it's for Antler 4. Okay, it's version 4 of Antler, and I don't know if that's also the 4th edition of the reference book, but you should always get the latest edition. Okay. All right. Okay. Okay. So we've already covered just about everything on my slides here. let me just zip over them. Okay, basic information, goals of the class. Now, a compiler class can end up being very theoretical, and I don't want it to turn into one of those types of classes. And we're not going to have time to get into the really advanced stuff. Okay, you will learn enough to be able to write a compiler. Okay, and okay, so working compiler, you'll be able to write sample programs in whatever language you choose to compile and be able to compile and run them. Okay, okay, lots of software engineering. Okay, so learning objectives, of course, you're definitely going to learn what a compiler is all about. And okay, I think we already covered all this in the syllabus. I do want to make sure the class has a lot of hands-on activities, so it's not just, as I said, not just a bunch of theory. Okay. So the first half of the semester, you're going to learn what parsers, scanners, interpreters, and language converters are all about. And I will give you a demo of this at the end of the hour. You'll learn Pascal. Now, the language that you will actually be writing your compiler in will be C++. Okay, so the implementation language will be C++, but the source language will be Pascal. So it's maybe a little confusing in the beginning, but it'll be clear as we get into it. And then, of course, Antler 4 is the name of the tool that we'll be using. Okay. Yeah. In the second half of the semester, we will take a deep dive into what compilers do, which is to generate object code. And the object code will be for the Java virtual machine. Now, you don't have to know Java, so don't worry if you're not a Java programmer. We're just going to use the virtual machine that Java runs on. Now, it has an assembly language. Okay, and so the low-level object code that your compilers will be generating will be the assembly language for the Java virtual machine. And you can download an assembler, which will then assemble that assembly code into binary code that can be executed. Okay? Now, the reason we don't have the compiler generate the binary code directly is that, well, the binary code is not human readable. And with the assembly language, at least you can tell what the compiler is putting out. Okay, so that's why we're doing this intermediate step of generating assembly code, and then we can run the assembler, okay, to generate the machine code. Okay, all right. Okay, this is the Antler reference. Okay, this is the recommended book. Okay, now the big difference in version 3 of my book is that it does not use Antler. And I've completely redesigned the class to have a stronger reliance on Antler. And so, as I said, I'm working on a new edition of the book that will make use of Antler. But so I'm using all of you as guinea pigs to make sure that this new way of teaching the class works. And last semester it worked out pretty well. So I'm sure it's going to go well this semester too. Okay. Okay, so you're going to form project teams, and so I'm going to leave that up to you to find teammates. Make sure that you use the discussion feature of Canvas for this class to look for teammates or to look for a team to join. Let's try to keep the teams to 4 members, okay? And then, as I said, for each of the assignments and for the final project, each team makes 1 submission, and all the teammates get the same score for that assignment and for the final project. Okay. Now make sure you choose your teammates wisely. Make sure that they're the people you can work with, that you all have good internet connections so that you can work together online. Once you form the team, then that's it for the rest of the semester. It doesn't work to have people jumping from one team to another. It's going to drive me and the grader crazy for us to keep track of all that. So make sure you form the right teams. Now, every semester, when I have a class where we have project teams, is that I'll have team members coming to me and saying that, oh, so-and-so never shows up, never contributes, okay? So you wanna make sure that you don't have that happen, okay? Make sure you don't put any slackers on your team, all right? Okay, project teams, and let me know by Wednesday. Send me your team name and a list of the team members and email addresses, okay? Only one person from each team needs to submit this, okay? So you're gonna submit this information into Canvas, okay? There'll be a place for that. Now, I always warn my students who are members of a project team that you should understand what's going on in the entire project, okay? Don't say that, well, I'm only going to work on this part and I don't have to worry about what the my teammates are doing, okay? As a hiring manager in my previous life, if I'm interviewing a candidate and I say, oh, I see on your resume that you worked on this project, so tell me how feature X worked in the project. And if you tell me that, well, I don't know because I didn't work on that part, then you are unlikely to be hired. Okay, so you don't want to tell a hiring manager that you don't know how a certain feature of your project worked because you didn't work on it, okay? Because you didn't work on that part. So even if everybody on the team has a particular part of the project to work on, you should know about the other parts too, okay? So that's your individual responsibility, okay? All right, I mentioned the postmortem report, and again, this is the how I weight the scores and how I adjust the scores later based on what your teammates tell me. And again, the B- is the median score, okay? All right, a couple of other things that I need you to submit into Canvas. The department wants a signed copy of the honesty pledge. So if you go into Canvas, you'll see a place for that. And then I'm also supposed to get a copy of your transcript where you highlighted the prerequisites, okay, which for this class, unless I got it wrong, is Compy 102 or Compy 126, okay? So these are things that the department expects me to get from you, and I'm supposed to drop students who don't meet the prerequisites. So let's make sure that you do, or you have permission from your advisor to take the class, okay? All right, I need to take roll, and the way I'm going to do that is I'm just going to, okay, dismiss this. This was yesterday. Okay, I'm just going to get a list of all 60 of you and just take pictures of that. I don't know how many I can get in one shot. Okay, it's going to take several shots. All right, hang on. This is actually easier than the old way where I read off students' names and butchered everybody's name. Okay, now scroll to here. Let's take another shot here. There'll be some overlap. I have to do this the first two classes. Oh, okay, and then, okay, I'll catch the remaining. right, take a roll. Okay, any questions so far? Okay. All right. Take roll. Okay, so let's talk about what a compiler is. Okay. So you know you can write programs in high-level languages. So I have a Hello World program in C++, in Java, and in Pascal, okay, which is this 40-year-old language. Okay. And you can see that, all right, each one of them will, when you execute it, will just write out, hello world, okay? And how does that all work? Okay, so let's take a look at the compilation process. So I'm going to start with this Pascal program. As I said, I'm going to use that as my sample source language. Okay? So hello.pass, okay, that's this file here. This is hello.pass, okay? And we feed it into a Pascal compiler, which is what we'll be writing. Okay, we're going to write this compiler, okay? And it's going to output an assembly language object program. So it's translate our high-level Pascal program into low-level assembly language. And the convention for the Java virtual machines assembly language is that it has the .j suffix. Okay? The J stands for Jasmine, which is the name of the assembly language for the Java virtual machine. Okay, and then you'll feed that into a Jasmine assembler, which you can download from the internet. Okay, and that will then generate a .class file, which is the binary object program, the machine language program, okay? And then you feed that into the Java linker and loader, which again will be provided for you. You probably already have that on your laptop. And finally, that will then run on top of the Java virtual machine, which you probably already have, and then that's how your program ends up executing. Okay, so a bunch of steps that you go through in order to take a program written in a high-level language like Pascal and get it down to machine code that the machine can execute. Okay, so there's a couple of translation steps here. Okay, this is translating from Pascal to assembly language, and this is translating assembly language into binary code. Okay, and then finally, all the way down here, you can execute the program. Now, just as a comparison, here is hello.cpp, the Hello World program written in C++. And of course, you run that through your C++ compiler, and that generates a binary object program, hello.o, the object code, and then you run that through the C++ linker and loader, and you get an executable file, which you can then execute. Okay, so here, okay, there it is. But you can run it right on your laptop or your workstation. Okay. So here we have translation. Okay. In fact, here is the command line you type in to do the compilation. Okay, and here is what you type in to do the linking and loading, and then here you are actually executing the program. Okay, so you can see that the way we're going to do it, we have this intermediate step here of outputting assembly language as opposed to outputting binary code directly, because we can actually read, we can actually read the assembly code to make sure that our compiler is doing the right thing. Okay? If we output binary code directly and something went wrong, you'd have a really hard time figuring out what went wrong because you wouldn't be able to read this binary code very easily. Okay? All right, so that's an overview of the compilation process. Now, of course, in this class, we're going to figure out what's in this box. Okay, so this is what we're going to spend the semester working on is the compiler. Now, in your compiler project, of course, you will probably pick another language. Okay, so either a subset of an existing language, or you're going to invent your own language. Okay, so that's up to your team. Okay. All right. Any questions? All right. So.
Oh wait, actually, yeah, I did have a question. So this is a small detail; it's not that important, but from my experience using the GCC compiler, when you want to, you can automatically just do g++ hello.cpp and then -o whatever you want to put the file name as, the executable as. So g++ hello.cpp -o hello, and then it will automatically create the executable hello. Like you
Yes.
don't have to do the -c part. Was that just like for explaining, like showing the
Yeah,
executable?
I wanted to show that two things actually occur. Now, when you don't do the -c, GCC will both compile and link, okay, and load. And I wanted to separate the two of them so that you can do a comparison with the diagram on the left. Okay, so that's why I deliberately did it so that it was in two steps. Okay. But you're right. You can tell G++ or GCC to do everything on one line. So.
All right, cool.
Yeah. Okay. All right. So what exactly is a compiler? Okay. Well, it is just software. I mean, it's not a magic box. Okay. And you know, it's extremely important when you're developing applications. And most of the time you take it for granted, right? It's there. Either you type in a command on the terminal to invoke the compiler, or if you're using CLion or Eclipse, there's a button that says compile, and you push the button, and then it happens. Okay, so you kind of take it for granted. Now, if your program doesn't compile because of syntax errors or whatever, then you notice the compiler, and you probably end up swearing at it. Gosh, all I did was leave off a semicolon, and you give me 2 pages of error messages, and so most of the time you take it for granted. Okay? And but what exactly is it doing? Okay, you give it a program that you've written. Okay, in Pascal, in C++, in Java, Python, whatever, some high-level language, and it translates it into a low-level language. Okay, and that could be assembly language, or directly machine code. Okay, and that's that diagram I showed earlier, where I showed the Pascal compiler generated assembly language, and the C++ compiler would generate the machine code directly. But in either case, it's taking a program you've written in a high-level language, and it translated it into a lower-level language. Okay? And the computer understands the low-level language. Right? It understands the machine code. Okay, so when the computer is executing your program, is executing the machine code that was translated from your high-level language. So it's just a translator. Okay? And now, in order to really get a good handle on what compilers are doing, in this translation process, I'm going to throw some terms at you. For example, source program. Okay, that's the program or application that you write in a high-level language, like Pascal or C++ or Java. And of course, you store that source program in a source file. Hello.cpp. That's a source file, or hello.pass. Okay, it's a text file. Okay, and so the source language is that language that you right? Okay, it's that high level language, Pascal, Java, C++, Python, or whatever. Okay, that's the source language. Okay, that's the language you write the source program in. Okay? Now the object language, okay, that's the target of the compiler. That's what the compiler is translating your high level language into. Okay, so it's also known as the target language. And so in our case, the target or the object language will be the assembly language. That's the low level language. Um, Other compilers like C++ will go directly to machine code. So it'll be machine code for like the Intel chip or the ARM chip. Okay. Now, I don't want people to confuse the term object language with object-oriented language. Yeah. Here, when we say object language, we are talking about the low-level language. Okay? Object-oriented language is a type of high-level language. Okay? So it can be confusing. I also teach Comp135, which is object-oriented language, which has to do with object-oriented languages. But here in this class, we talk about object language, which is the low-level language that the compiler produces. Okay, so the object program then is your source program translated into this low-level object language. Okay? Now the target machine is the machine that's going to execute your object program. Okay? And quite often, of course, the object machine or the target machine is the same machine that you use to write your high level your program in the high level language. It's all the same machine, but target machine says that okay, the compiler is producing low level language for a particular machine. Okay? In our case, we are producing low-level language with a Java virtual machine. So that's our target machine. If you look at G++ or GCC, well, it's producing low-level language for the Macintosh or for your PC or whatever machine that you're working on. So that will be your target machine for that compiler. Okay. And then finally, the implementation language is the language that you write the compiler in. So in this class, we're going to be writing our compilers in C++. Okay, so we're going to use C++ to write a compiler that will compile Pascal, okay, or at least my examples in class. Okay, and you're going to write a compiler for your projects in C++ to compile whatever source language your team chooses. Okay, so there's a bunch of terms here, and I know it may be a little confusing initially, but I will be using these terms, okay? And they'll be clearer as we go along. Okay, so we now know that a compiler is basically a translator. What else can compilers do? Okay, well, compilers allow you to write in high-level language, right? Without compilers, you wouldn't be able to write in C++ or Java or Python or any of these wonderful high-level languages because compilers are required to translate your high-level language into something that the machine can execute, okay? Compilers provide language portability, okay? By implementing a compiler, let's say that, okay, let's just talk about C++, okay? There are C++ compilers that run on different models of computers. A C++ compiler that runs on a Macintosh, one that runs on Windows, one that runs in Linux, okay? Each of those compilers, even though they're separate programs, they work with an industry standard version of C++. So there's an industry standard that says that C++ programs have these kinds of statements, and here's the syntax of the statement. Here's what each statement means. And so the compilers are implementing the standard, which means that, well, theoretically at least, you can write a program and you can compile it and run it on different machines. So you can write a game program that you can compile and run on the Macintosh, and that same game program will compile and run on a Windows machine or on a Linux box, because the compilers, the C++ compilers on those machines implement or compile the standard C++ language. Okay? Now, if of course you decide to use non-standard features, let's say that the C++ compiler on the Macintosh has a special feature and you take advantage of it, then if you try to compile that program on a Linux machine, it may not compile. So you really have to be careful to stick with the standard language and not use any special extensions. And it's the compilers that allow that portability, that if you stick with the standard language, the same program should compile and run on different machine architectures. Okay? A compiler can actually improve your program, and that is usually optimization. Okay? So you write your program in high-level language, okay, and you compile it. So other than translating it, the compiler can try to improve your program in certain ways. It can try to optimize the object code for speed. So that means that the code that the low-level code that the compiler generates is optimized for speed. Okay, so the compiler does whatever it has to do to make that program run faster. Okay? Or it can optimize your program for size. Okay, let's say that you're dealing with a machine that has limited memory, maybe is some sort of embedded chip, and so you want the compiler to generate low-level code that is as small as possible. Okay, so that's another form of optimization. Okay. Now maybe your compiler is generating low-level code for a mobile device, and you can optimize the code for power consumption, right? You want to make sure that the code will use as little power as possible so it doesn't drain the battery, okay? So different ways that a compiler can optimize the code. And there are combinations. For example, the C++ compiler, you can optimize for speed, you can optimize for size, or you can do a combination, like some sort of compromise between speed and size. The bottom line, of course, is that whether the program code has been optimized or not, it should run and produce the same results, right? You don't want to optimize a program so that it runs 10 times faster, but runs incorrectly, okay? So you don't want the wrong results 10 times faster, okay? So optimization is an important part of compiling. And at the end of the semester, we'll talk about optimization, okay? All right, now it's all about translation. And so far I've been talking about translation from a high-level language like Pascal or Java or C++ to a low-level language, okay, such as assembly language or machine code. There are other forms of translation. There's a form of translation called conversion, where you translate from one high-level language to another. So for example, since I'm going to use Pascal as my example source language, I can write a converter that will take a Pascal program and convert it to an equivalent C++ program. Okay, that's a conversion. Okay, there's also interpretation, where I'm translating a high-level program to actions. In other words, I'm just going to directly execute the program. So instead of going through a low-level language like assembly language or machine code, an interpreter will just take your source program and translate it into the actions. In other words, they will just execute the program. And that's interpretation. Okay? So we're actually going to do all three of them. Interpretation, conversion, and compilation. Okay, so compilation then traditionally means taking a high-level language program written in a high-level language and translating it down to a low-level language. Okay? All right, I'm going to do a demo of all three of them, and by the end of the semester, you will actually be able to do what I'm about to show you, okay? And you're going to do it for your language, not just for Pascal. Okay? All right, so I'm going to bring up Eclipse. I like to do my work in Eclipse. You can also use a C-Lion. I've tested everything out in C-Lion, and that works too, okay? All right, so here is a Pascal program, okay? And you can see that the name of the program is hello. It has a variable I, which is a type integer. It's got a for loop that's going to go 5 times and write out hello world 5 times. Okay, so very simple program. This is what Pascal looks like. Okay, so I'm going to interpret this program, which means that I'm going to translate this program directly into the actions. Okay, so let's see that happen. And so that's execute. And okay, oh, there it goes. Okay, you see that there it is. Okay, it writes out hello world 5 times. Well, it also writes out the value of I and the string hello world. And so there it is. Okay, so there is direct execution. Okay, this is known as an interpreter. Okay, now I also do a few other things. I print out the program again. This is a listing of the program, and you can see that there are several passes involved. Pass 1, I checked for syntax errors. There were none. Pass 2, I generate a cross-reference table. Well, there's only one variable called I, but it shows up in lines 4, 7, and 8. Okay, here's 4, 7, and 8. And I say that, well, I is a variable. It's at nesting level 1. You'll know what that means later. And it's a scalar, and its type is integer. Okay, so information about the variable. And then finally, in the third pass, I execute the program. Okay. All right, so this is what it means to translate a program into its actions. And this type of translation is what an interpreter does. Okay. Now I'm going to show you a converter. I'm going to convert this program, okay, written in the high-level language Pascal, into another high-level language, C++. Okay, so let's do that. And let's convert. Okay. Now, the first 2 passes are the same. I get the listing, no syntax errors, just semantics again. But now in pass 3, instead of executing, I've generated hello.cpp. And we should take a look at that and see what it looks like. Let me do a refresh here. And okay, where is it? There is hello.
It's a bit higher, like under the intermediate folder.
Oh, there it is. Yes, very good. Okay, and let me open it. And gosh, this is the program translated into C++. And you can see a few things here. Okay, here's I, variable I. Here, actually, let me split the screen here so you can see both at the same time. Okay, so here's variable I, and here's that for loop. Okay, so there it is. And then the right line got converted into a printf. Okay, and I should be able to compile and run the C++ program with the C++ compiler. And to do that, I need to move it into another project because now I'm going to have two main programs. So this is a main, and then of course, the compiler code had a main. So let me move it into another project. And so here is hello.cpp. Drag it down here. All right, so now I should go to run this from here. And they're compiling it, and whoop, there it is. Okay, so there's the output again. Okay, I also, you see here that when I do the conversion, I added some statements here to do timing. So this is really the guts of the program, okay, along with the variable I. And the rest here is just to get this timing. Okay, obviously this thing went so fast that it took almost no time at all. Okay, all right, so that's the converter. And finally, I'm going to show you the compiler. Okay, so now I'm going to compile this into low-level assembly code. And you'll see that. Let me close this. Okay. And all right, so here, compile hello.pass. And the first two passes are the same. And now I've got hello.j. Okay, remember .j is the for the Jasmine assembly. Okay, now again, I have to refresh this to make it show up. Hello, refresh. And oh, there it is. And this is the program in assembly language. Okay, now, right now it looks like totally cryptic, but believe it or not, by the end of the semester, you'll be able to read stuff like this. Okay. Now, what can I do with this assembly code? Okay. I'll notice that as comments here, I do try to print out. Okay, let me again split the screen here. I do try to print the original source line. And so here is the for statement, line 7. This is for statement. Okay, it got kind of scrunched together, but then underneath is the assembly code for doing the for statement. Here's the write statement. And here's all the code for doing the write statement. Okay, actually, this code here is a combination of the for statement and the write statement. Okay, all right, well, what are we going to do about this? Well, we can certainly assemble it and run it. Okay, so let me, I need to go out to the file system and find that file. So hang on just a second here. This is Pascal CPP. And then you can see in here, there is, there's hello.j. Okay, so I need to open up a terminal window in this directory. So now watch me do this. Okay, so now I'm open up one of my terminal windows. I'm in this directory. If I do ls*.j, I should see there's hello.j. If I do cat hello.j, you'll see that, okay, it's that program that I was showing you inside of Eclipse. Okay, and I'm going to assemble it using the Jasmine assembler. Okay. It produces hello.class, which is the binary code for the Java virtual machine. And so I can run this Java hello, and there it is. Okay, so you can see that with a compiler, you end up with this intermediate step of the assembly language, which we then assemble to get the machine code, and then we can finally run the program. Okay, so you've seen this program run 3 different ways. Number 1, interpretation. Then number 2, where I converted it to another high-level language, which I then compiled and ran. And then here I've compiled the Java program into assembly code, which I then assemble and then run. Okay, so you've seen all 3 of them, and you will do all 3. Of course, ending with the compiler. Okay, That's the ultimate step, is to be able to generate low-level assembly code. And that's what people usually mean when they talk about compilers, is generating low-level object code like this. Okay. All right. I hope everybody's excited about, gosh, by the end of the semester, I can do this. Either that or people get scared. So, all right. Well, in order for us to make any progress at all, you're going to have to learn Pascal. And this is a language that your parents learned when they were learning programming, or maybe your grandparents by now. That's kind of scary. There are these two tutorials that I mentioned earlier. Either one of them will do. And now there is an online, well, your first assignment will be to write some Pascal programs. And in fact, let's take a look at that. Let's see here. Go back to the class page, and this first assignment is here. So you're going to write, program 1 is to write a program that writes out "Go Spartans" 10 times, okay? And then you're going to write a program that merges two arrays. And the third program is a little bit more involved. You're going to read in an input file that has names of presidents, and the instructions will tell you what you're going to do with this data. Okay. Now, in order for you to do this, of course, you need a Pascal compiler. Okay. Not the one that I've written, but one that's online. And so there are 3 links here for 3 online compilers. I really like the third one, so I'm just going to go there. And oh, there it is. And you can see that it starts out with a sample program, and it's already filled in with a sample program. But you're going to type in your program, or cut and paste into it. And then when you type execute, then it obviously will compile and execute that program. So here it only wrote out 1 line. So here's the output line. Okay. And then if it's a program like the third one that has the data about the presidents, you would cut and paste that into this window. Okay. And so actually, give you a hint that, okay, let's take my hello program here. Copy, paste, execute. Oh, and there it is. Okay, so you have a way of testing out your Pascal programs that you're going to write for assignment number 1. Now, assignment number 1 is the one and only individual assignment. Okay, so I want each of you individually. Oh, wait a minute. Hang on. What did I say? Maybe I changed my mind on that. Hang on. Let's make sure I'm telling you the right thing. Oops. Where am I? Yeah, this is the individual assignment. So each one of you, because I want everybody to really know Pascal. But future assignments will all be team-based. So by the time assignment 2 comes around, you should all be in project teams. Okay. All right, that's your first assignment. And let's see if there's anything else I need to say. The class ends in what, 5 minutes? Okay. Okay, this is the wrong set of slides. I keep doing this. 152. Okay, so reminder, by Wednesday, you can tell me what your teams are. Okay. Okay. Any questions at all about this class? Okay. I hope you're all excited. I know it's kind of scary, and everybody tells me that, oh my God, writing a compiler. That sounds really scary, but believe me, you will by the end of the semester be able to do it. Okay. All right, I have a few minutes left. Are there any questions, first of all? Okay, and I did mention that I will have office hour at 4:30. So, and I did send out the Zoom invite for that. Okay, but let me also point out that I have this grant. Okay, let me find where I am again. Okay, so if you go here, you see that I list job openings at NASA. Okay, and I have a grant for job openings for student interns. Okay, unfortunately, because of the pandemic and the fact that Ames is locked down, there aren't too many internships opportunities available. But hopefully, when we get past this and Ames opens up again, I'll be able to hire students for internship positions at NASA. And the grant that I have is to pay for the students to work as interns. Okay, but I also have listed here full-time positions. So if you're graduating and you're looking for full-time work at NASA, I also list a few openings. I got 3 more openings, and I haven't updated this webpage yet. So that's something that if you're interested in working at NASA, before I gave it all up to teach here at San Jose State, I was a senior scientist at NASA. I can tell you, it's really, really fun place to work. And if you want to work with really, really smart people doing some really cool things like, landing rovers on Mars, which is what I did. And yeah, now we're trying to go back to the moon. All kinds of cool stuff going on at NASA. So if you're interested, check out this webpage. Okay. See, some of the positions are already filling up, and I'm getting new full-time positions. Hopefully, I'll also get some internship positions. Okay. All right. Any other questions about the class? Okay. So go ahead and form your project teams. Use the discussion feature of Canvas to define teammates or teams to join. Okay. All right. Any questions? Okay. You're all quivering in your seats. I hope you're not. Okay, then I will go ahead and end the meeting, and we'll come back and see you next Tuesday. A question?
Yeah, how do we submit the assignment? Do you want us to do a screenshot?
Oh, it will be in Canvas. I forgot.
Oh, okay, I got it.
It will be in Canvas. I forgot to do that. I should probably do it right now. Okay, so I will open it up in Canvas.
Thank you, Professor.
All right. Any other questions? Okay, then I will end the class and see you all on Tuesday. Okay.
Thanks, Professor.
All right, have a good day.
All right, you're welcome.
Thank you, Professor.
All right, you're welcome.